morning. I am going to be using the same notes for both classes, the physics and the honors physics, because the material is basically the same. There's not any difference between what I'm going to be teaching you. So in the other physics, this is actually chapter 20. So let's go over some basics of the information. We're going to be talking about the atom. The atom is made up of the nucleus and the electrons. The nucleus contains the positively charged protons. It's the most massive part of an atom. I need to move this up a little bit. So the mass is attributed to the nucleus, whereas the size of an atom is attributed to the electron cloud. And we're going to do this pretty quickly. You've had this, so you should have been able to read it over. Neutral object has the same number of electrons as protons. You learned that in chemistry. One or more electrons can be removed from an atom by adding energy. So for instance, if you had a plastic comb and you were to take a cloth and rub the cloth over the comb, it would become electrically charged. And you could pick up little pieces of paper. Energy is released when an ion is formed. And you can't remove a proton from an atom by ordinary means. If you remember, that's a strong nuclear force, and it is the biggest force of all the four basic forces. Conservation of charge. You can't create or destroy charge. You can only transfer it. You move them by, like with a balloon. If you rub it against your hair, you're removing electrons. Different ways you can remove electrons with different types of examples, which I have that stuff at school. I can't show you. Okay, when a neutral object loses an electron, it becomes positive. If it gains, it becomes negative. Insulators. Materials to which electrons will not flow easily: rubber, plastic, wood, cloth, air, and glass. And then the opposite would be conductors. Materials will flow, or electrons will flow smoothly through them without much delay at all. All metals, basically. Semiconductors fall in between silicon and germanium. They use those a lot. Air is a good conductor, but forces produced by strong charges can rip the electrons off. That is plasma and lightning. Two types of charge, positive and negative. Charges exert forces on each other over distance. Like charges repel each other, unlike charges attract, much like magnets. Neutral body can be charged by bringing it into contact with a charged body. That's conduction. Neutral body can be charged if you bring it near. That's induction. Conductions are actually touching each other. Induction, they are not. This is an important, moving on, Coulomb's law. Coulomb's law looks a lot like the gravitational force equation. If you remember that, it's F is equal to G m1 m2 over d squared. Sometimes we use R, sometimes we use D. Okay. K is the constant that we will use in order to make this equal. K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Newtons, coulombs, and meters are the units that will be there. The charge of an electron is 1.6 times 10 to the negative 19th, and that's also a negative charge. So I'm going to put a little negative in front of that. Coulomb is the charge of, in 1 coulomb, there's a charge of 6.25 times 10 to the 18 electrons. These are reciprocals. Electric force is a vector quantity. Positive gives us repulsion, and negative gives us attraction. Okay, just like that. Here we see representations of electric fields. Electric fields. The charge flows out of a positive and into a negative. So if you were to look at this, it says, is this positive or negative? It's positive. And this one is negative. And what's happening is C a positive charge or a negative charge? Well, the charge flows out of a positive towards a negative. So C is positive, D is negative. Looking at these, it's coming into E, so E is negative. F is going away, so it's positive. And if you look at these, as it gets stronger, the lines get closer together. These are all repelling each other. This is going out, going out, going out. These are all positives. The direction of electric field is away from a positive charge and toward a negative charge. When the field lines are closer together, the field is strong. And if you have different charges, will bend the lines. You can see how they're bent. Field lines are imaginary. These are just drawn for visual effect. Electric field intensity. E is equal to the force on the test charge. We usually use the test charge divided by the test charge, newtons per coulombs. The direction of the field line is away from the positive towards negative. And here's another formula. Electric energy and electric potential. Electric potential, usually we use a delta V, potential energy divided by the charge. And there's another formula. The electric potential in a uniform field. Uniform field exists between two parallel metal plates. D is the distance between the two metal plates. V is equal to, we're not going to really worry very much about the negative sign. Okay. You can read this over. Storing charge is a capacitor. Energy can be stored in a gravitational field by increasing the potential energy. A good example of a capacitor is a flash. What happens is it builds up the charge and then it releases the flash, and then it builds up the charge so that it can release flash again. Potential energy, you can look this up. We're not going to really go into that. Capacitance is Q over V. A capacitor is a device that will store a charge, usually plates separated by an insulator. All of your keys on your computer are capacitors. They have a different amount of space between, or different codes that they emit when they're pushed. So I will take a picture of this and let you have this. These are the equations that we're going to be looking at. Let me just, that was a sound effect, by the way. Like I said, I'm going to take a picture of this so you can see it. This is just a reiteration of all of the formulas that we will be using. Now, what I would like to do is I would like to do the example problems. Hopefully you were able to print them out, because I can't, for some reason, print these out. So I have them on my computer, and I'm going to be looking at them while I do them for you. Okay, let's take a look at number one. Number one says a negative charge. I'm going to make sure that you can see that. There we go. A negative charge of -2 times 10 to the -4th coulombs and a positive charge of 8 times 10 to the -4th coulombs are separated by 0.3 meters. What is the force between the two charges? So this is going to be the F is equal to K, Q sub 1, Q sub 2. Let's just go ahead and use D's for all of these, so that way we won't get confused. So this is going to be 9 times 10 to the 9th. The first charge they told us was -2 times 10 to the -4th. The second charge was 8 times 10 to the -4th. And they are separated by a distance of 0.3 meters. Set that all up, and the answer is negative. Now I want you to think about this for a second. If it is negative, is it attracting or is it repelling? It is attracting. Okay, I didn't do all of the write out all of what everything was. I'll do that this time. A negative charge for number 2 of negative 6.0. Oh, I know, and it says 0.0 on your form. Change that to negative 6.0 times 10 to the negative 6 coulombs. It exerts an attractive force of 65 newtons. Attractive force, 65 newtons. If it's attractive, do we assign it a positive or negative? Since it's attractive, we're going to call it negative. That is 0.050 meters away. What is the magnitude of the second charge? In order to do this, you have to manipulate this equation and solve for Q2. And when you do that, you will have F d squared over K Q1. Now it's all just a matter of substitution. So we have negative 65 times 0.05 divided by 9 times 10 to the 9th times negative 6.0 times 10 to the negative 6. And you'll see what's going to happen here is this is going to become positive. This is positive because they're attracting. One has to be positive and one has to be negative. And I get about 3 times 10 to the 6, and the unit is coulombs. Now you have to be careful here because there's C's and Q's and all different kinds of letters all over the place. Some are units, some are unknowns. Okay, let's take a look at number 3. A positive test charge of 5 times 10 to the negative 6 is in an electric field. So this is an electric field problem, and I've spelled field wrong, apologize. That exerts a force of 2 times 10 to the negative 4 newtons. What is the magnitude of the electric field at the location of the test charge? We're looking for E. We have a really nice equation for this. Very simple to use. E is equal to F over Q. We have the force divided by the charge, and we are going to get 40 newtons per coulomb. So the electric field, there are 40 newtons force on every coulomb of charge. Number 4, a negative charge of 2.0 times 10 to the 8th coulombs experiences a force of 0.060 newtons to the right in an electric field. What are the field's magnitude and direction at that location? All right, magnitude is just what the quantity of it is. And we are looking to see that E is equal to F over Q again. So it's basically a substitution. E is equal to 0.060 divided by negative 2.0 times 10 to the 8th. And that is going to be negative 3 times 10 to the 6 newtons per coulomb. And that is going to be directed to the left. Directed to the left. All right, number 5. What is the magnitude of the electric field strength, so we're looking for E, at a position that is 1.2 meters from a charge of 4.2 times 10 to the negative 6 coulombs? All right, so we have another formula that we will use. It is a combination of this formula up here and this formula here. It will be E is equal to K Q divided by D squared. And we have everything we need. K is a constant, 9 times 10 to the 9th. Q in this case is 4.2 times 10 to the negative 6th over, and this is where people might make a mistake. They might make the mistake in forgetting to square. The answer to that is going to be 26,250 newtons per coulomb, or since we have 2 sig figs, 2.6 times 10 to the 4th newtons per coulomb. All right, let's see if we can get number 6 on this one. What is the electric field at a position that is 1.6 meters east of a point charge of positive 7.2 times 10 to the negative 6? We are looking for E again, and we have D and Q. So this is going to be exactly the same type of problem. 9, I'm not writing the formula again, it's right up above. And this was really easy to do on my calculator because I already had all this information from before. I just changed up the numbers a little bit. That is going to be 2.53, or we could just do 2.5 times 10 to the 4th newtons per coulomb, and that is going to be east because it is going to be away from the positive charge. Okay, moving on. Number 7. The electric field intensity between 2 large charged parallel metal plates, a capacitor basically, is 6,000 newtons per coulomb. The plates are 0.05 meters apart. What is the electric potential difference between the two of them? So the electric potential change is delta V, and we have a formula. Delta V is equal to ED. Simple problem. It's just going to be 6,000. There's my refrigerator, my ice maker. That will be 300 volts. It seems weird because we're starting off with a V and we're getting that as the unit, but that's the way sometimes these things work. Number 8. A voltmeter reads 400 volts. Its potential difference across 2 charged parallel plates that are 0.020 meters apart. What is the electric field between the two of them? Okay, we're just going to manipulate this equation to get E. It's going to be the delta V over D. 400 divided by 0.02, which is 2 times 10 to the 4th newtons per coulomb, but you'll notice that this would have been volts per meter. Either one of these would be acceptable unit. And number 9. What work is done when 3 coulombs, that's a charge, is moved through an electric potential difference of 1.5 volts? We have another equation for this one. W is equal to Q delta V. Substitution. These really aren't that difficult, just figuring out what is what, because the formulas are pretty basic, and a lot of this you can do in your head. Does anybody remember what unit work is? Give you a second. Joules, that's correct. I miss you guys. Number 10. A 12-volt car battery. So the potential difference is going to be 12 volts. can store 1.44 times 10 to the 6 coulombs. That's the charge when it's fully charged. How much work can be done by this battery before it needs recharging? Same formula as above. W is equal to 1.44 times 10 to the 6th times 12, which is 1.73 times 10 to the 7th joules. That's how much work it can do before it needs to be recharged. Number 11. I'm going to do number 11. I'm going to need my calculator. Number 11, an electron in a television picture tube passes through a potential difference of 18,000 volts. How much work is done by this battery before it needs recharging? Okay, we need Q. Q for an electron is negative 1.6 times 10 to the negative 19 coulombs. So work is going to be negative 1.6 times 10 to the negative 19 times 18,000. Let's see if the calculator will turn on for me. My battery is low. It needs recharging. Ironic, isn't it? .88. W is equal to Q delta V. Boy, there's not a lot there. 2.88 times, ooh, just got really windy here. Negative 15 joules. Okay, let's move on. And number 13 is our last. Nope, number 12. We're on number 12. Number 12, a 27 microfarad. I've got 12 twice there, by the way, and I think I had 10 twice too. Apologize for that. This is capacitance, and I know we use C for coulombs, but C is also for capacitance. So it's 2.2 times 10, 27. I'm looking at number 13. So this is actually, I apologize, 27 microfarads. We don't use micro though, so this is going to be 27 times 10 to the negative 6 farads. We need to change that. And it has a potential difference of 45 volts. We want to find the charge. So Q is equal to, kind of funny, QVC. Q is equal to delta VC. I always remember that because of QVC. Right, go ahead and find that. It's going to be 45 times 27 times 10 to the negative 6. And that's going to be in coulombs. And the answer, look real quickly here, is 1.2 times 10 to the negative 3rd. Now, I know I forgot the negative sign. That would be work done on it. That's why it's negative. I'll put it there. Okay, one more. Number 13. Guys, it's snowing here. Oh, my Lanta. Someone's playing a cruel, cruel joke on us. Okay, number 13. The capacitance is 2.2 microfarads. Its charge to the electric potential difference is 6 volts. How much additional charge is needed to increase the electrical potential difference to 15. Okay. I want to find out what the change in charge would be. So the change in charge is actually going to be the capacitance times the change in voltage. So we have the capacitance is 2.2 times 10 to the negative 6, and the change in the voltage is going to be from 6 to 15. So I'm going to do 15 minus 6. And that is going to be 2 times 10 to the negative 5th coulombs. Now, I know, guys, this is crazy. The C's are all over the place on this. You just have to keep into perspective what you're being asked and what the unit will be. And you'll always have that formula sheet in front of you, so that should help. I will be uploading a problem set probably around the same time that you see this video. I hope that you guys are all doing well. Again, I miss you guys like crazy. Today is the last day to order your yearbooks. If you're a senior, send me information on where you're going to college, because I'm doing the senior wall in my basement. And please take care of yourselves. Bye.